In this video, we'll look at a method for solving homogeneous linear differential equations. So we'll begin with an example, and this example will be of the second order. So we'll begin with the second derivative of y with respect to x. And then we can also have lower order derivatives, so first derivative of y. And then we can have terms that just involve y itself, so minus 6 times y. But this is homogeneous, so it has to be equal to 0. In a situation like this, we can try the following solution. Try to find a solution of the form y equals e to the power mx, where m is some constant. Then we can substitute that solution into the differential equation and then see if it works. In order to do that, we need to compute the derivatives of our solution. So we'll take the first derivative, and that's equal to m times e to the power mx. And take the second derivative, and that's m squared e to the power mx. And now we'll substitute those into the differential equation. So first we have the second derivative, and that's from over here, m squared e to the power mx. Then plus the first derivative, which is here in the middle, m e to the power mx, and then minus 6 times y, which is e to the power mx. And now basically what we want to do is to find the value of m that will allow the left side to all add up to becoming 0. So we'll see if we can factor this left side. There's a common factor of e to the mx in each one of the terms, and that can be factored out. So it'll give us e to the power mx times m squared plus m minus 6, and that's equal to 0. Well, we can keep on factoring. So the m squared plus m minus 6 factors as m plus 3 times m minus 2. So now we have our left side completely factored, and we can start working on solutions. The first thing we should notice is that e raised to a power mx can never be equal to 0. So this first factor will not lead to any solution. But we have here m plus 3 could be equal to 0, or m minus 2 could be equal to 0. And we get two different solutions, m equals negative 3 or m equals 2. Now recall where these m's came from. We had originally proposed it up here that y equals e to the power mx is a solution for the differential equation. So we get two different solutions down here. There's y equals e to the power negative 3x, or y equals e to the power 2x. So we have these two solutions, and in fact they are independent solutions. You can tell they're independent because if you look at e to the power 2x, there's no constant you can multiply by this e to the power 2x that will turn it into the other solution, e to the power negative 3x. So these two solutions are not, one's not a linear combination of the other. They're independent solutions. Now furthermore, we know that since we started with a second order differential equation, then we'd only expect to get two independent solutions in a fundamental set of solutions. So really this is our entire fundamental set right here. We can write down the general solution for the differential equation just by taking a linear combination of the two solutions that we have. So I'll take a constant c1 times the first solution, e to the minus 3x, and add a constant c2 times the second solution, e to the power 2x. So that's a general linear combination of the two solutions in our fundamental set, and it's for a second order differential equation. So this is a complete list of possible solutions for the differential equation.